So today we are going to discuss about Maxwell's relationship. What are the Maxwell's relationship are important in the metallurgical thermodynamics perspective. So for that we are going to introduce certain fundamental equation and the concept of Helmholtz free energy as well as Gibbs free energy. So if you want to understand what is Gibbs free energy and what is Helmholtz free energy, for that we first want to know about the concept of thermodynamic potential, because both these free energies are important thermodynamic function. You can tell them thermodynamic potentials. Thermodynamics potential are basically a state function. What is state function then? State function is always depends upon the or description on the basis of initial state and final state of a system. So it does not bother about the path of the process. So this is the basic features of this state function which differentiate those function from the path function. So now you can formally tell that thermodynamic potential are state function that if you make them together with the corresponding equation of state, those state function or potentials can describe the equilibrium behavior of a system as a function of natural variables. Then we have to understand what is natural variables. The natural variables, you can tell that are a set of appropriate variables that help you or allow you to compute or evaluate other state function by partial differentiation of the thermodynamic potentials. So these variables are going to help you by using other state function and performing partial differentiation of the thermodynamic potential in order to evaluate certain different state functions. So this is the most important things. Till now what we understood? We understood that in order to know basically the Gibbs free energy or Helmholtz free energy, we have to understand the thermodynamic potential, because those free energies are basically thermodynamic potential, and thermodynamic potentials are basically the state functions. And then we have to understand what is state function. State function depends on initial state and final state of a system. So how it differs from the path function? It differs from path function because it has a very striking feature, only considering initial and final state, not bothering about the path of the process. So now what is thermodynamic potential? It actually helps to describe the equilibrium behavior of a system as a function or depending on the natural variables. And what is the natural variables? Those variables which are going to help or allow to evaluate or compute or determine other state function by using partial differentiation on the thermodynamic potentials. So now we have to understand the difference between the Gibbs free energy and Helmholtz free energy. So first of all, we should know that Gibbs free energy is basically energy available to do some work. Both are, because free energy is defined by the energy of a system which is available to do some work. So what is the difference in the Helmholtz and Gibbs? The Gibbs energy is the energy available to non-PV work in a thermodynamically closed system at constant pressure and constant temperature. What does mean? It means that if Gibbs energy concept you are using, you are taking automatically thermodynamically closed system which is at constant pressure as well as at constant temperature. And this Gibbs energy is actually intended to do non-PV work or available for performing non-PV work in a thermodynamically closed system at constant pressure and constant temperature. Whereas if you think about Helmholtz free energy, is actually maximum amount of useful work, although that is non-PV, that may be non-PV, that can be extracted from thermodynamically closed system at constant volume as well as at constant pressure. So difference is that both are having same system concept, the thermodynamically closed system. What is the closed system? Because there is no mass transfer will be allowed, only energy transfer can be done. So based on that, only the difference you can see that it is the Helmholtz energy is for constant volume and Gibbs energy for constant pressure, and both are for constant temperature. But the another word is that here Gibbs energy is available energy to perform non-PV work in a thermodynamically closed system at constant pressure and constant temperature. But here the concept is different. For Helmholtz free energy, it is telling that maximum amount of work. So it is related to little bit of internal energy concept is most important, and in case of Gibbs energy, enthalpy concept is most important. So in the slide you can see now the what is Helmholtz free energy. It is A equal to U minus Ts, absolute temperature T, S is entropy, U is internal energy, and A is the Helmholtz free energy. And the same way if you can represent the Gibbs free energy, G, capital G equals to H minus Ts, where H is enthalpy, T is absolute degree temperature, and S is entropy. Now, for a thermodynamically closed system, the state functions, if you can understand the state functions and you can represent with a certain fundamental equations, you can see that if it is an internal energy and internal is a function of entropy and volume, and differential of the internal energy is the exact differential. Why is it so? Because internal energy is a state function. So that's why we are able to take du as the exact differential or perfect differential. Then we are going for ds and pdv. So all are state functions. So we are taking perfect differential. Same way h, a and g, if you can represent, dh is a perfect differential and ds and dp. So dA same way minus s dt minus p dv and dg equal to minus s dt plus v dp. Now if you represent those things in the dA equal to del A by del T at constant volume dt in this way, in this formulation, all those things already you have done previous lecture. If you can do that based on the understanding of the process, because here you are talking about certain thing is constant, so this can be in the partial differentiation. And already we told that if you want to determine another state function based on the existing state function and thermodynamic potential, you have to perform partial differentiation on that thermodynamic potential. So okay, so you are doing the same thing in the expression. Now, if you go for the calculation, dA by dt at constant volume equal to minus s, dA dV at constant temperature is minus p. It's already, you can see that things. Now, you can del T same way at constant pressure minus s, that is the s is entropy, del G del P at partial differentiation at constant temperature equals to volume. Now, this is a Maxwell relationship. What is Maxwell relationship? We have to understand first. Maxwell relations, you can tell that it's a collection of equation or a set of equations in the domain of thermodynamics, which can be derived from the symmetry of second derivatives and from the definition of thermodynamic potential. So regarding the thermodynamic potential, already we understood what it is and how it is related to state function and how it is related to or dependent on the natural variables. Okay, but regarding the second derivative symmetry, we have to now focus. If you see in this expression, del square A del V del T equal to del square A del T del V. This is the thing where in the denominator you can switch del V and del T because this is a symmetrical second derivative. Same way you can represent G with respect to symmetrical second derivative. So such kind of symmetrical second derivative you can derived from this kind of concept, and then also if you are using the thermodynamic potentials, then you are going to get the Maxwell relations. We'll understand later on. Now if you see these two things, if you equate that way, you can understand this equality or expression you can, or identity you can derive. Now one question we can bring to in the mind, or we can focus on, that if we can know the Gibbs free energy as a function of absolute temperature and pressure, can we represent everything in the thermodynamic domain? Or more crude way you can tell, we can know everything. You can know everything if you know that capital G as a function of temperature and pressure. So this concept we have to understand, because then only you can understand that Gibbs free energy, how important it is in a thermodynamic domain, or if you want to interpret one system thermodynamically, then you can have this kind of concept, that if we know the Gibbs free energy as a function of temperature and pressure, then we can know everything, or it is not true. So for that we have to understand. We know the entropy is equal to minus del G del T at constant pressure, and if we go for volume, then del G del P at constant temperature. So these two things there. Now what are the different thermodynamic potential or state function we are having? Suppose if we start with enthalpy equal to G plus Ts, and we put the S, that expression del G I del T at constant pressure with a negative sign, and we multiply with the absolute temperature, then we are going to get this expression. And if you represent internal energy, U is equal to H minus PV, and H equals to, what is H? H equals to, already we derived from previous expression, capital G minus T multiply with del G del T at constant pressure minus capital P into del G del P at constant temperature. The same way, if you go for Helmholtz free energy A equal to U minus Ts and A equal to G minus P dGP dt. So even Helmholtz free energy also can be expressed in the terms of G as a function of temperature and pressure, and temperature you must think temperature is in the absolute scale. And another two expression you can see, if you want to also derive the Cp, the heat capacity at constant pressure, then it is T into del S by del T, and in the place of S, if you put same expression del G del T at constant pressure with a negative sign, again we are getting an expression. Only if you know the G as a function of temperature pressure, then you can evaluate Cp also. So, and for particular temperature or pressure. So then we can tell that we can get all the functions from G as a function of absolute temperature and pressure. This is a very important concept because it actually helps us to understand the significance of Gibbs free energy as a function of absolute temperature and pressure. Now we are applying these things for the different matter or state of matter. Suppose G is a function of T and pressure. temperature in absolute scale, and pressure is the, if you can tell, the natural variable, and G is function of those two variables. For liquid state, for solid state, and gas phase. Okay, now if you can write that V equal to del G by del P at constant temperature, that is the correct expression. Now we want to understand what is the effect of pressure or variation of pressure on the variation of G, capital G, that gives free energy. So if we look at the thing in the liquid and solid, we can tell that with respect to pressure, the change in volume will be negligible or very small. So we can neglect. The assumption is very practical and realistic. So we can write that G is a function of T or and P2 is equals to G is a function of P1 plus V2 minus V1. So if the change in volume is very small, so we can tell that the Gibbs free energy is for the liquid and solid state of matter. It is basically function of only temperature in absolute scale. So we can ignore the effect of pressure for liquid and solid state if we are going to determine the Gibbs free energy. So we can tell that for liquid and solid, Gibbs free energy is a function of temperature in absolute scale. That is quite realistic, and the assumption to reach that expression is very practical and realistic, as for such kind of state of matter, the change in volume with respect to change in pressure is very, very minimal. Now, on the contrary, if you check ideal gases, then things are different. They are dependent on the pressure, so, and temperature as well. So now you can see the Gibbs free energy is the both dependent on the pressure and temperature, and that's why you can also see that also if you check the entropy is the del G by del T at constant pressure. That also dependent on the particular temperature as well as the during the process what is the pressure. So if you want to understand that the concept of internal energy, how it works and how it is going to give the concept of the perfect differential and all those things. So if internal energy for a hydrostatic system, the combined first and second law, you can write du equal to TdS minus PdV. So U is a function of S and V, entropy and the volume, and both are natural variables. And already we understood what is natural variable. Again, we can tell that natural variables, you can say that natural variables are a set of certain appropriate variables that allow you or facilitate you to compute or determine other state function through the partial differentiation performed on the thermodynamic potentials. So these are the basic nature of, this is the basic nature or basic definition of natural variables. And the U is a function of entropy and volume, which are natural variables. Then expression you can represent like that, du of S and V, du ds, del U del S at constant volume into ds, and is constant entropy del U del V. If you multiply with the du, dv, you will get. So as du is exact differential, and you can write this expression just del V del U del AU del S V equal to just switching that, and in this way you can reach this kind of expression. Now it is related to certain mathematical representation or mathematical calculations. So we have to understand what are the differential form and how the differential interpretation one can do in mathematically. So for that we for any state function. So if you check a state function, suppose function of xy, where independent variables are x and y. These two are independent variables. And now what will happen with the state function xy if you want to represent them that function in a differential form? And since it is a state function, then df will be exact differential. In the left hand side, df what is written, it is a differential. And then if you do partial differentiation of the function of xy with respect to x, when you are taking y is a constant, then it will be a function of xy, and you can take that a of xy and it multiply by exact differential of the x variable dx. In same way, del f del y at a constant x, you can multiply with the exact differential of y and is a function of xy. Of xy based on which function of xy you are chasing, then it is the b of xy. But these two functions will be different. That's why you are taking in the first part a of xy and b of xy. So both are function, both may be the function of x and y, the independent variable x and y, but they are different function. So this very nice mathematical feature of the combined first and second law of the thermodynamics is that when u is expressed in terms of the particular variables s and v, and already we understood s and v are natural variables. Now, if you consider, we have some systems having three variables such as x, y, and z. So we can define any of these as a function of other two variables. Suppose x is a function of y and z, y is a function of x and z is a function of x and y. So x can be represented as a x of y and z, y of x and z of x and y. So now if you want to take that kind of expression as a state function represented just previous slide, but we have dealt with during the function of xy, we are representing a perfect differential or differential form. Here also same thing, you can represent dx equal to del f x and y at constant y into dy and del of x and del x and del z at constant z dz, and that del y del x at constant x if you talking about dy, the perfect differential form of y. So this is the way you can represent mathematically. And in this process, we are considering all thermodynamic parameters are functions of the natural world. So this kind of representation can be implemented in all the kinds of thermodynamic parameters or functions, and which are the functions of natural variables. Okay. Now we have to understand now thermodynamic potential versus equation of state. The natural variable of u are s and v, which means that if the function of u of s v is known for a given system, suppose you know a function u of a natural variable es and v, entropy and volume, then we can get all the thermodynamic properties of the system via differentiating u and v. The equation of state then will be u, and u is a function of t, v, and n. Now del u by del t at constant volume, it's a cv. Del u by del v at constant temperature, dt dp del t at constant volume minus p, if you represent such a way. Here another another simple thing I want to say, one concept I want to introduce, that is response function. What is this? Response function is basically, it can be obtained by second order differentiation of internal energy. If you go for del square U del S square, because U is a function of V, S and T, and at constant volume and number of particles, then you can write del T del S at constant volume and number of particles. It's equal to T by CV. So if you see, same thing we are doing here in the expression. If you check that, if you del U del T and if you go for U equal to S comma V and N, then the expression what I am discussing about, that will be done. So you will get double differentiation of U if you want to represent that things. So in this way, if you go for double derivation differentiation of U, just you can remember that it is a concept of response function, and it actually obtained by double differentiation of internal energy. Now we are going to understand the classical mechanics and the difference with the thermodynamics. So if you check the internal energy as a potential for the condition, this is a thermodynamic potential, then classical mechanics, it takes as a potential energy which a position vector of that x, y, z. And what are the independent variable for the classical mechanics? X, y, z. But here the independent variable is entropy, volume, and number of particles, SBN. And dependent variable in classical, you have to get the gradient of the potential energy or any energy. Then you are going to calculate the effects kind of concept. Here you are going to get the gradient of internal energy with respect to different natural variable. Suppose del U will be at constant. So this is pressure, dependent variable. So now most important thing, in order to understand, represent, and memorize and to remember the Maxwell relationship, and again we'll repeat what is Maxwell relationship. Already you know, this is basically a set of certain equation, and in a thermodynamic sector, which are derivable from symmetrical second derivatives or from the definition of the thermodynamic potential, and it is named based on J.C. Maxwell, the Maxwell relationship. But you have to understand how to remember it and how to easily represent it. So for that, mnemonic diagram is very helpful, and it can be very useful to construct Maxwell relationship. So if you see the diagram in the slide, the differential expression for the thermodynamic potential and Maxwell relationship, you can conveniently remember in terms of certain schematic diagram like thermodynamic mnemonic diagram. And this diagram, if you see, it is in the shape of square. So it's a square diagram. So you can tell that the diagram consists of a square with two diagonal arrows pointing upwards. And if you see more closely, the thermodynamic potential in alphabetic order are in clockwise on the side if you see the figure. And the natural variables, if you are identifying the natural variables, they are associated with each potential placed at the corner of the diagram, the square block. If you see the square diagram, the corner, all the corner are they associated with the natural variables. Now, if you see diagonal arrows, that actually indicates the coefficient associated with the natural variables in the differential expression of the potential. So again, I am repeating the statement. The differential expression of the potential, if you are talking about that, it can be constructed based on the understanding how diagonal arrows here are playing the role. Diagonal arrows indicate or show the coefficient associated with the natural variables and in the differential expression of the potential. And if you want to determine or identify the sign of the coefficient depends on whether the arrow is pointing upward or away from the natural variable. If the arrow pointed upward, means it pointed toward the things. Suppose if the arrow is pointed towards from P to V, so for the V, you have to take the sign negative. So if the arrow pointed towards, then the sign will be negative. And if the arrow is pointed away from the natural variable, then sign will be positive. Now, if you want to take an example and to understand, in order to understand the diagram or the nature of the diagram, how we construct, take a concept of internal energy. So du. Now du is a function of that the perfect differential, two differentials will be there, ds and dv. So du, you are constructing this side, and it is ds and dv, this axis ds and dv. So now we have to find out the sign associated with the ds. So the arrow is the pointing away from the s, so the sign will be positive. We are taking positive sign. And if you take the coefficient at the sign of dv, this is a pointing towards the v, so that's why the sign is negative. Now coefficient, what will be the coefficient for ds? If you are checking the coefficient of ds, how you can determine? Now from the s, the arrow is reaching to what natural variables, that is t. So t will be the coefficient, so tds. And if you see v, the arrow is connected or coming from p, so p will be the coefficient. So in this way, sign and coefficient of the equation you can construct. And if you want to construct, then you have to take the state function or thermodynamic potential, and then the same axis which are the corner of the things, there will be the perfect differential variable. First you have to write those things, then you check how the direction of the arrow is towards the variable or away from the variable. Based on, you choose the sign, and then you can subsequently determine the coefficient. Now, thermodynamic potential of a system with a variable number of particles should depend on mu and n, the chemical potential as well as the number of particles. And along with that two things, you have to take care of thermal variable as well as mechanical variable, which can be, you can, for a gas, you can see that thermal variable S is extensive and AS is extensive and capital T is intensive, and mechanical variable V is extensive and capital P is intensive. Now what we have to understand, what is extensive variable and what is intensive variable. Extensive variable are those variables which are dependent on the mass of a system or amount of mass or matter present in the system. It is that thing, if it is governing the variable, or the variable is dependent on the mass or amount of matter of a system, then such variables can be termed as extensive variable, such as entropy. And if you go for volume, also is the extensive variable. But if certain variables are independent of mass or matter of the system, then you can tell them the intensive property or intensive variable. Those are capital T, temperature and pressure here. So thermal, these two variables and these two variables all are important to understand our thermodynamic potential of a system, because those are playing important role to influence the thermodynamic potential of a system. Now if you check this diagram, this is a schematic or pictorial representation of understanding what we have learned. Gibbs enthalpy, you can tell that Gibbs free energy, and free energy here you can tell that it is a Helmholtz free energy. So if you check, suppose you are talking about intensive variable and extensive variable, we just differentiate or categorize in two columns. Pressure is the intensive variable and capital T is also intensive variable, as already we know, and entropy and volume is extensive variable. Now, if you want to know about Gibbs free energy or internal energy, we start with the internal energy, since here it is internal energy. So internal energy is a function of entropy and volume. So it is a function of extensive variable volume and extensive variable entropy, and it itself is an extensive variable. Means it depends on the amount of matter present in the system or mass of the system. Now we will come to Gibbs free energy. Gibbs free energy, if you check here, it depends on both temperature and pressure. Both are intensive variables, and Gibbs free energy itself are intensive variable. Here it is written this enthalpy. Now you can check enthalpy. Enthalpy, but in this case it is dependent on one intensive variable, that is pressure P, and another extensive variable S, that is entropy. So it is depending upon two variables. One variable is a dependent on the matter of amount of matter in the system. So it is a different function. It is not absolutely intensive characteristic or absolutely extensive characteristic. Same way you can see the Helmholtz free energy is a function of one intensive variable and one extensive variable. Here it is represented, and here only the extra term n is presented. Okay, so the four basic thermodynamic potentials we have understood. Now these four thermodynamic potential, if you put in a summarized form of Maxwell relationship, and then you can get this kind of expression. If you go for differential form, this is that you can tell dF or dA. I interchangeably use that F and A for Helmholtz free energy. Other things are already known. So this is the summarized tabular representation of Maxwell relationship.